Alright, this is question 8 of the homework from homework number 4. So for A, one of the first confusing things may be what is the verge on moving. The verge on moving just means that the force being pulled matches exactly with the static friction force. So that means it's not moving and it's at the max of the inequality. So once you understand that, this problem is relatively straightforward. We know how to find the force of friction. It's just normal force times by the static coefficient of static friction has to equal the force that's being pulled. But in this case, we can write normal force as the weight, which is given to us. But you have to remember, this guy is also pulling it up. And when he's pulling it up, he is weakening normal force by F times sine theta. Why sine? Because the opposite over the hypotenuse is this y part right here. This is what he's pulling up. So you have to minus y sine theta. And then the force in the x direction, in this case, is this adjacent to this angle right here, which is this vector, which would make it F cosine theta. So then you plug in your numbers into the weight minus F times sine theta, all times by the coefficient of static friction should equal F cosine theta. And then you go through the work and you should get an answer somewhere around here, depending on your numbers. And for B, in class he did tell us this, which is the way to tackle questions like this is to use tan theta equals the U static friction, or whatever friction the question's asking you. So you can skip forward, or if you want me to explain, I'll be including this part in. It'll be a little lengthy. So we know that friction force equals the U static force times normal force. And when it reaches the maximum, before it starts moving, the static force is exactly equal to the pull force. So I'll be using them interchangeably here. So in normal force, remember that normal force is directly related to gravity. And for gravity, you may remember it as mg. But technically, gravity is just mg cosine theta. Just look at our box and ramp problems for that. The reason why we often don't say the cosine theta is because on flat ground, cosine theta is 0 and cosine 0 is 1. But this is actually very important to remember because in this case we're pulling up. So, and then let's talk about the friction. Friction always opposes movement. But since we use positive mg cosine theta, we use the same sign for the frictional force. Technically, we can make them both negative. So what I'm doing here is that I'm rewriting this frictional force equals static force times normal force into sine theta, mass times acceleration, because I'm just using the box and ramp as an example. You could use a flat surface if you wanted to. It's the same. Times by static friction times by cosine theta mg. This cosine theta replaces the normal force essentially, and this sine theta replaces the frictional force, because the frictional force and the force that's sliding is the same. So force equals ma. We have this ma and this mg here, but they'll cancel out because remember, gravity is just an acceleration. So we can simplify this further to get sine theta equals U static friction times cosine theta. And then if we just divide both sides by cosine theta, we get our formula. Tangent theta equals US. This will give you the minimum angle. This is the general formula, and this is how you find it. Now for C. Luckily C is pretty easy. You just find the theta that you got from B and plug it into the same equation from A. Except just plug in the new theta. You should work it out, and you should get a number that is smaller than the number you got in A. Remember, it should be smaller.